Hello everyone, and welcome back to another episode of Central Physics Reviews. I'm super excited for this episode because we finally get to talk about dynamics, which is the study of the laws of physics, or the rules that govern the evolution of a system that we kind of were just handed down and took for granted when we did kinematics in the past couple episodes. The first thing that we have to talk about in this discussion, though, is what the state of a system actually entails. So that way we know what it is that we're trying to determine the behavior of. And when we did kinematics, we noted that the state consists of not only a particle's position, but also its velocity. And so here we get to talk a little bit about why that actually is the case. So to begin this discussion, we should probably talk about what it means to have a state of an object, right? And in particular, what we mean when we say state is we mean the set of properties that are intrinsic to a system, right? So we can write down intrinsic properties of a system as opposed to the properties that describe its interaction with other systems or the external world or the environment, if you like. So as a test to see whether some property of a system is actually part of its state or not, what we can do is imagine the system in a perfect vacuum with nothing else to interact with, right? And we can ask ourselves, is that property going to be maintained by the system in the absence of any interactions? And it should be pretty straightforward to see that in the case of position, for example, if you bring a particle to outer space or any vacuum and there's nothing around to interact with it, and you put it down in some position, maybe we can call it some vector x relative to an origin, then that particle will maintain that position, and so we can of course consider it as part of the state of the particle. Something that might be less obvious or less intuitive is that if you put a particle in a vacuum and you assign it some velocity vector, so let's say you say that it's moving to the right at some velocity v. In the absence of any interactions, this particle will maintain that property. It will keep moving to the right at the same velocity v, and that's not necessarily a principle that can be derived from something, but it's a physical law that comes from observations of the universe around us, right? This is just a pattern that we see in nature, and we call it Newton's first law, or Newton's first law of motion. And this is simply the recognition that in the absence of any interactions, a particle will maintain a constant velocity vector over time, right? So this fact of nature is why we treat velocity and position as components of the total state of the particle. Now, unlike position and velocity, the acceleration of any system is actually a fleeting property. It's not intrinsic to the system, but instead it's a direct result of interactions of the system with something outside of the system. So for example, if I were to put a particle in a vacuum and I were to quickly accelerate it, so I would give it some acceleration vector a, maybe by pushing on it or something like that, and then I quickly went away, so it had nothing left to interact with, that acceleration vector over time would actually go to 0 over time, or maybe I should write in the absence of interactions. And this property, that the acceleration of a particle depends on interactions while its position and velocity are intrinsic to it, is the reason that when we study kinematics, we evolve, or we look for the trajectory of its state, meaning the position and velocity, when we're given some sort of acceleration. In other words, when the system interacts with something external to it, we want to figure out how the system will evolve over time. Now, you can, in principle, consider other properties of a system, like its color, its shape, or its orientation, that are also going to be intrinsic to it, but in most cases, properties like a system's color aren't going to be changing over time, and so we can generally ignore them, basically knowing in the back of our minds that we know how they evolve over time already. They stay constant. That's generally what happens. Now, orientation is actually something that in some systems, in spinning systems in particular, does change over time. And that's a topic of rotational motion that we'll actually tackle separately in a later episode. But for now, our scope is just going to be limited to defining the state of a system as its position and its velocity, which I should have really marked as a vector here. There we go. And our goal for this episode will be to look at what kinds of interactions will cause the system to accelerate, and how do we quantify how much it will accelerate. And the way we do this in physics is actually pretty straightforward. All we end up doing is looking at systems and observing them, doing experiments, and quantifying patterns that we observe so that we can write down what acceleration corresponds to what interactions in the world. And these correspondences are exactly what we refer to as the laws of physics. So in the case of gravitational interactions, the resulting acceleration is actually quite simple. The acceleration vector is given in magnitude symbolically by gm over r squared, and I'll explain what these variables mean in a second. And then the direction of the acceleration is a unit vector that we'll call minus r hat. So let's go over what all of this means real quick. Let's start with the direction. R hat refers to the unit vector pointing from the external source of gravity toward our system. So for example, if our system is to the left of the external source of gravity, then r hat is a vector pointing left with magnitude 1. That's why it's called a unit vector. And the fact that this acceleration of our system points in the opposite direction of r hat is a reflection of the fact that gravity is an attractive force. So it will always point toward the external source of gravity, right? So if this is r hat, then minus r hat points in the opposite direction toward whatever is interacting with our system gravitationally. Now, the magnitude of this gravitational acceleration is controlled by just 3 variables. The first is actually not a variable at all, it's just a constant. So this g is Newton's gravitational constant, and it's equal to approximately 6.7 times 10 to the minus 11 in SI units, and that would be meters cubed per second squared per kilogram. The variable m represents the mass of the external system, so maybe I'll just label it m external, so that's what's attracting our system of interest. And r itself is the distance between our system and the external source of gravity. So for example, in our picture over here, this distance over here is what we would call r. And what you'll notice, the reason that I said that the acceleration in the case of gravitational interactions is relatively simple is that this acceleration vector doesn't actually depend on any properties of the system itself, right? If you know the mass of the external object, whatever is attracting your system gravitationally, and you know how far away it is from your system, you automatically know how your system will accelerate in response to that interaction. On the other hand, practically every other interaction in nature will result in accelerations that depend on properties of your system itself. So as an example of that, we can talk about the electrostatic interaction, which is an interaction between 2 charged particles, that's what electro refers to, that are at rest, which is what static refers to, right? And the law of physics in that case is that the acceleration of your system will equal 1 over the mass of your system, so already properties of your system are coming into play, multiplying another constant k times the charge of your system times the charge of the external object that's interacting with your system, divided by r squared. And this time the direction is positive r hat. And that's a reflection of the fact that if you have 2 charged particles whose charge is the same sign, so either 2 positive charges or 2 negative charges interacting, then that interaction will actually be repulsive, not attractive like gravity, right? Like charges repel, but opposite charges attract, because if one of these charges is negative while the other is positive, then you can obviously see that the direction of this acceleration will turn into minus r hat, or attractive. Now, I should mention that Coulomb's constant over here has a value in SI units of 9 times 10 to the minus 9, and so that's going to be kilograms times meters cubed per second squared per coulomb squared. And coulombs are just the SI units for charge. And these units definitely aren't something that I remember off the top of my head, but you can easily derive them by just rearranging this equation and solving for k, and then figuring out what the dimension is of everything on the other side of the equation. And so really, with some of these equations and interactions in mind, the name of the game when you're doing physics becomes, first you look at what your system is interacting with, then you use the laws of physics to figure out in what way those interactions make it accelerate, right? That's where these equations come in. And then you go back to the skills we learned when we talked about kinematics to figure out how that particular acceleration vector will evolve the state of your system over time. That's the process that we have to go through when we're basically doing physics from scratch. And in principle, you don't need anything else. You can do all of physics only working with three variables: acceleration, velocity, and position. And of course, time, right? Time is, in the Newtonian framework, just some background variable that keeps ticking forward. But there is another variable that will be really convenient to introduce, both for intuition purposes as well as for, just writing down more concise physical equations later, and that is the force variable, right? So this idea of forces was first introduced by Isaac Newton, and basically the concept here is to, instead of speaking about accelerations, you describe the world, you formulate your laws of physics in terms of the product of acceleration and the mass of the system that's being accelerated. So that's ma on the right-hand side here, and you call that combination, that product, a force. So that's the left-hand side here. And of course, we should talk about the units of force, right? Well, first we should mention that it's a vector. It's just literally a scaled up version of acceleration. But let's also talk about the units of force in SI units. We're going to have units of force equaling the units of mass times the units of acceleration. And so in SI, that's going to be kilograms times meters per second squared. And because that's a bit of a mouthful to write out, that's defined to have its own letter, its own symbol, N, and that stands for newtons. So if you don't feel like saying you're measuring forces in kilogram meters per second squared, you can equivalently say you're measuring it in newtons. But let's go back, let's take a step back and talk about why we're defining forces in this way to begin with. And the way I see it, it really is a definition, right? This equation, F equals ma, is Newton's second law of physics, or second law of motion, I should say, Newton's second law. But I see it as less of a law of physics and more of a definition of what a force is. And so the reason that it's convenient and useful to define force in this way is that for everything except gravity, like we mentioned, the acceleration of a system, very crudely speaking, went something like 1 over the mass of the system multiplied by some strength of interaction. And this was true for the electrostatic interaction that we talked about, right? So there the acceleration was 1 over m times kqq over r squared. And it's also true more generally, again, as I mentioned, for anything but gravity. And so when we define this force quantity to be the mass of our system times its acceleration, what that means is that ma, this product, will basically represent the strength of whatever interaction is occurring. So crudely speaking, this product, or the force as we will call it, is basically a measure of how hard you're pushing or pulling on something, how strong that interaction is, without considering the mass of that object, without considering its resistance to acceleration. So in terms of this new language of forces, we can write down the same laws of physics that we had before, but now, for example, instead of writing down the acceleration due to gravity, we can instead write down the force due to gravity. And that would be equal to the same thing we had before. So we have the g, we have the mass of the external interacting object, but now we're also multiplying through by the mass of our system to get the force. And then we're still dividing by r squared. Everything else is the same. We still have the same direction, which is minus r hat. The only difference is that now we've multiplied through by the mass of our system. And analogously, if we want to talk about the electrostatic force, multiplying through by the system's mass gets rid of that factor of 1 over m that we used to have out front for the acceleration. And so all we're left with is k times the charge of the system times the charge of the external interacting object divided by r squared. And this one's in the r hat direction. And right away, you can see that one thing that's useful about talking about forces in terms of accelerations is that now these two different things, gravitational and electrostatic interactions, actually look very similar, right? GMM over r squared and KQQ over r squared have the same exact kind of ring to it. And that's not just a feature that makes these equations look nice, it's also something that's going to prove useful when we're doing physics in the future. And again, by useful, I just mean it'll be convenient to work with forces instead of just accelerations. Now, of course, I don't want to give the impression that gravitational and electrostatic interactions are the only kinds of interactions you can have, right? You can also have electrodynamic interactions, which come from charged particles that aren't static, that are moving around. You can have magnetic interactions, and these are things that we're going to talk about in future episodes. Some of you might have even heard of something called the weak nuclear interaction, the strong nuclear interaction. And those are actually something that we're not going to talk about in this context because the weak and strong nuclear interactions occur on such small scales, right? On length scales of the nuclei, which are something like 10 to the minus 15 meters across, that the framework of Newtonian physics we've been discussing actually doesn't apply anymore. You have to discuss these interactions in the context of quantum mechanics, where even the definition of what a state is totally different from here. So that's why I don't even like to call them weak and strong nuclear forces, because this whole concept of forces is a Newtonian construct that no one really talks about when you're doing physics in the context of quantum mechanics. So for what we're doing, which is purely going to be Newtonian physics, we're going to be concentrating on gravitational and electrostatic interactions, and again, at some point, electrodynamic and magnetic interactions will also come into play, and those have their respective force laws, which tell you how those interactions make systems accelerate too. Now, I do want to take a pause here and point out a really important feature of these force laws and interactions in general, which is that they don't ever actually depend on the explicit position of your system, right? Notice that in the case of gravitational or electrostatic attraction, they only depend on the relative position between your system and whatever external system is interacting with them. What this means, for example, is that if you observe an airplane directly overhead in the United States, and you have a friend in Europe who describes that airplane with a completely different position vector, the two of you can still agree on the laws of physics and how that airplane will accelerate over time given its interactions with its surroundings. Because both of you will agree on all of those relative positions, even if you don't have the same position vector for each object. Similarly, when we get to electrodynamic laws and magnetic laws that do depend on the velocities of objects, you will find that they only depend on relative velocities. Meaning that if you see that airplane moving very, very quickly, and you have a friend in the airplane who sees the airplane as stationary relative to them, the two of you will still agree on the laws of physics because you'll agree on every relative velocity between that plane and other objects around it. The only so-called reference frame in which these laws of physics won't be the same is if the reference frame itself is accelerating, or in other words, if you, the observer, are accelerating. Because if that's the case, then from your perspective, everything around you will appear to be accelerating in the opposite direction, even if it's not interacting with anything. And so unless you adjust the laws of physics to account for your own acceleration, you should really only be doing physics from a reference frame that isn't accelerating itself. Anyway, that was a bit of a long tangent, but let's get back to the main point of this story here. If you're given the laws of physics in this form, meaning you know the forces corresponding to various interactions rather than the accelerations themselves, the only thing that changes is that in order to calculate the acceleration of your system, which is simply the sum of all of the acceleration vectors corresponding to each interaction that your system is undergoing, what you have to do now is recognize that each of those individual accelerations is actually just a force vector divided by the mass of your system. And so to find the total acceleration, all you have to do is find the total force, right? Sum up all of these force vectors over all interactions that you have, and then divide that sum by the mass of your system. So conceptually, if you know that your system is interacting with another system gravitationally, and a third system electrostatically, what you would do is use the laws of physics that we've written down here to find the force on the system from each interaction. Then you add those force vectors together and divide by the mass of the system to get you the acceleration of the system. And then, just like before, you can do kinematics with that acceleration to figure out how the state of your system will evolve over time. Now, I have to admit that there's one obvious shortcoming of this whole process, which is that the force laws we've written down, right, this law for gravitational interactions and this law for electrostatic interactions, rigorously speaking, they only apply for interactions between two particles, right? We're talking about the mass of one particle and the mass of another when we write down external and system. And we're talking about the charge of one particle and the charge of another particle when we write down Q external and system. And in the real world, interactions we observe aren't just between two individual particles, right? The systems that we're used to seeing in everyday life are comprised of countless particles that are all interacting with each other in far more complex ways than these simple equations can capture. And so what we have to do is we have to get a little bit more creative or a little bit more clever about how we handle those situations where our systems are comprised of many particles and the objects that they interact with are comprised of many particles. Now, for the sake of keeping this video under an hour long, that's something that we're going to have to dive into more in the next episode. But in the meantime, the last thing that I wanted to talk about is this idea of Newton's third law of motion. And this is where we actually get a lot of the payoff for talking about physics in the language of forces instead of just accelerations. Because when we're talking about forces, Newton's third law can be formulated in a very concise, powerful, and intuitive way. But before we get to the punchline, let's motivate Newton's third law a little bit by considering two particles in the vicinity of each other, labeled 1 and 2 here, that are interacting gravitationally and electrostatically, right? So I've written out 4 equations. The top row represents the two forces felt by the first particle, one gravitational and one electrostatic. And the bottom row represents the forces felt by the second particle, one gravitational and one electrostatic. You'll notice that they're the same equations we had before, gmm over r squared and kqq over r squared in each case. And the directions are given by these unit vectors. So the first particle will feel a gravitational force in the direction of particle 2, but it will feel an electrostatic force in the direction of particle 1, meaning away from particle 2, assuming the charges, Q1 and Q2, carry the same sign, right? Because like charges repel each other. Similarly, particle 2 will feel a force in the direction of particle 1 gravitationally, but it will feel a force in the direction of particle 2, or away from particle 1, electrostatically. Okay, so that should be intuitive. And there's a really interesting relationship here where r1 hat, meaning in the direction of particle 1, is by definition equal to the opposite of r2 hat, because r2 hat means in the direction of particle 2, which is the opposite way, right? And similarly over here, r2 hat is equal to minus r1 hat. These are the two opposite direction, right? r1 hat points from particle 2 to 1, and r2 hat points from particle 1 to 2. And by recognizing that fact, we can actually rewrite the forces felt by the second particle as minus gm2 m1 over r squared r2 hat, and the electrostatic force will be minus kq2 q1 over r squared r1 hat. And what you'll notice is that q2 times q1 over here, for the force felt by particle 2, is actually the same product as q1 times q2 that goes into the force felt by particle 1, right? These forces are products of both the system and the external charge. Similarly, the gravitational forces are products of the system and external mass. And because they're products of these two quantities, the actual magnitude of the force remains the same whether you're talking about the force felt by particle 1 or the force felt by particle 2. In other words, what this means is that the gravitational force felt by particle 2 is equal to minus the gravitational force felt by particle 1. And the electrostatic force felt by particle 2 equals minus the electrostatic force felt by particle 1. And Newton's third law goes beyond this. It extrapolates this pattern, and it suggests, based on observations of patterns in nature, that even if you're not talking about just two particles, even if you're talking about massive systems made of many particles in the most irregular shapes you can imagine, whenever they're interacting with each other, the force on one system, F1, will always be equal to the opposite of the force on the other interacting system, F2. So that means that if one object ever attracts another object, the other object will also attract the first object right back. If one object ever repels another object, that second object will repel the first object right back. Indeed, in the same way that the Earth is attracting you down to it right now, you're attracting the Earth up to you. And perhaps the reason that you don't notice that in everyday life is because your acceleration under that amount of force is relatively high because your mass is relatively low, whereas the Earth's acceleration up toward you is low because the Earth's mass is very high. But the two forces of attraction between you and the Earth are still equal in magnitude. One of the most important consequences of Newton's third law, this experimental or empirical observation about the world around us, is the conservation of momentum in any closed system. And what that means is that if you have two particles interacting, or really any two systems interacting, momentum can only be transferred from one system to the other, while the total amount of momentum in both systems stays the same. So let's briefly derive why that's true, right? By definition, momentum, which is labeled by the variable p, is equal to the mass of a system times its velocity. And of course, velocity is a vector, so momentum is a scaled up version of that vector. And in fact, you'll notice that momentum is to velocity the same thing that force is to acceleration. And in fact, if we write out that the force on object 1 is equal to the mass of object 1 times its acceleration, dv1 dt, and we equate that to minus m2 dv2 dt, we'll notice that that's the same exact thing as writing that dp1 dt is equal to the opposite of dp2 dt. And that just comes from the fact that this constant mass in front of each derivative can actually be absorbed into the derivative. And so instead of multiplying the mass by dv dt, you can just take dmv dt. And of course, mv is the momentum. So by combining the two sides of this equation, we can actually write that the derivative of p1 plus p2, this is a vector sum, with respect to time, is actually equal to 0. And conceptually what that means is that the quantity p1 plus p2 doesn't change over time no matter what forces or interactions are at play. So what happens is if you have a set of particles that are all interacting with each other, and you have to be careful to make sure that your set includes every particle involved in these interactions, then if you sum up all of their individual momenta, you will get a vector, the total momentum vector, that cannot change over time unless something from outside of that set comes in and transfers its momentum to your set of particles. Now, I know this has been a ton of information, so let's go ahead and summarize the most important key points of what we've talked about so far. The first thing we said when we were defining the state of a system was that position and velocity are inherent properties of a system. If you have a system that's interacting with absolutely nothing, and it has some initial velocity, that velocity won't change over time because that velocity is just a property of your system. On the other hand, the acceleration of any system is a property of its interactions with the things around it. A system in a vacuum without anything to interact with can't possibly accelerate as a whole. Next, we went over a couple of laws of physics that told us what that acceleration is, or what that force is, if you like, corresponding to some particular interactions. And Newton's third law told us that whenever those interactions occur, both interacting systems feel equal and opposite forces, meaning that the total momentum of both of those interacting systems stays the same throughout the interaction. I hope you guys learned something and enjoyed this discussion of the laws of physics that govern our universe. If you did, leave a like on this video. If you have any questions, leave a comment down below. and I look forward to seeing you all in the next episode.